Campbell's going to start speaking, but this is a tag team talk like the day is, and so I'm going to turn it over to Brian here.
Yeah, we thought we were going to be very edgy by having 3 people speak, but apparently that's just normal now. So Angus and Thomas are going to speak as well, but this work involves quite a few other people. In particular, I'd like to mention Thomas Sewell and Ricardo Amilda, who have done a lot of the work on this. So we all know from the last couple of days that instruction set specifications are very large. The ARM A architecture is coming into hundreds of thousands of lines of specification now. When you're thinking about these specs, there are kind of 2 rough types of reasoning that you want to do about them. One is where we have some machine code in our hand, and we want to verify that machine code has some property, probably actually does what we wanted it to. And the other one is where we don't, we're just going to run some arbitrary code, but we want to check that the architecture protects certain properties. So usually security properties or safety properties. They don't, that we have memory isolation or something like that. And we don't necessarily want to handle these in the same way, though I think Dominic might object to that in the next talk. But yeah, he can do that. So in particular, we are interested in ARM's experimental Morello architecture. The rough idea of this is it takes the ideas that have been generated through the Cherry project at Cambridge to add hardware capabilities to existing architectures. So it's a kind of backwards compatible way. What do these capabilities do? They give you extra metadata for every pointer that you have. It tells you which bounds it's valid within, which permissions you have, so you can read and write, that sort of thing. And especially, they are unforgeable. So there's a separate little stash of memory which contains special tag bits that tell you whether or not a capability has been legally constructed. So you're limited in what you can do to one of these things without losing your unforgeable bit. And this stuff looks very, very good. It gives you, one of the main things it gives you is very strong memory protection. And you can, if you've got something like a large pile of C code, mostly just recompiling it works. There are a few places where you've done horrible things and you need to atone for your sins. But generally, most stuff just recompiles. And the Microsoft Security Response Center have taken a look at the Cherry scheme and reckon about between 1/3 and 2/3 of vulnerabilities that they see would be mitigated, which means roughly they are thinking they wouldn't have to ship a security patch if all they cared about was Cherry-style architectures. And they haven't, during this project, ARM haven't just thought about the architecture, they haven't just thought about the microarchitecture, they actually went and built some. So they took the Neoverse N1 processor, which at the time was high performance, and they've got even higher performance ones now, but not with Cherry in them. And they actually built some processors, built some boards, and they look like this. So you've got these nice press photos, there's a chip which has the processor in it, they come in boxes like this, and maybe you don't believe that press photos are real, though apparently the engineers were quite upset about having to take the heatsink off for that one. So here's a real crappy smartphone photo demonstrating that there really is one in my office, together with the project's paperweight. With for some reason, I think they had some dead processors left over or something, and they decided to make some nice mementos. So what does the specification look like? Well, we've already mentioned before that there are these ARM specifications in their architecture specification language, particularly the one that Alistair is using, Intel. And they actually wrote a specification, saving us a lot of bother, incorporated into the base ARM v8.2 specification. So this is taking the existing specification, they added lots of Cherry stuff to it, they adapted many of the operations, and came up with a complete specification for the architecture. And you might notice that the number of lines in this slide are rather lower than some of the other things. So that's partly due to the age of it, they didn't have some of the vector extensions then, and partly because they did a very sensible thing of leaving the entire 32-bit architecture out of it. And I was very glad about that, because it's really annoying. And this wasn't just a one-off thing, they were providing us with snapshots weekly whilst they're developing the architecture, whilst they're writing the RTL for the actual processor design. So we got to see this stuff live, we got to provide feedback, we got to do some work on it before they actually built the real thing. And so what do we do with this? We automatically translated it using tooling that we already had for translating ASL into our SAIL language, which the other Alistair described the other day. And so it gets a bit bigger in the process. And we didn't just do this once. We did it whenever they gave us a snapshot, and then we looked at updating proofs and other work just to check that when they changed stuff, they changed what we were expecting them to, and what we thought was true still held true. And so this is an example of some SAIL code that we generated from the ASL. Everyone loves to give a bit of arithmetic in one of these examples. And so this is an add instruction, but it's an add to a capability. So this is basically a pointer arithmetic operation. And so instead of calling a normal add function, you call this cap add. And it's doing a bunch of work underneath to check that you haven't violated any of the safety constraints around the bounds of the capability. Because if you go too far away from your allowed range, the compression scheme breaks and you lose your unforgeability bit. And there's some other stuff as well, some stuff to do with the feature I haven't told you about called sealing. And there's some technicalities to do with the stack, whether you're talking about stack pointer or a regular register. And all of these things are included. And there's also this thing getting it up to check that you've actually turned capabilities on, because you can just use this thing like a normal ARM processor as well. So once we've got it into SAIL, well, we have a big bunch of tools. So it joins these other architectures up at the top, and when we get out, we've got our emulator tool, some emulator tooling, some symbolic execution tooling down here, which was originally developed for concurrency, though there hasn't been any concurrency work in this project. Some stuff for doing theorem proving stuff, and some documentation things we also don't need in this project because ARM already produced an entire manual for Morel, which is presented as a supplement to their normal one. And what we're particularly interested in is these green bits at the bottom. These are some of the things we're going to produce. The other question is, why do we believe this model? So ARM wrote it, that's a good start, but people make mistakes. Sometimes they make mistakes in the design of the hardware, sometimes they make mistakes in the design of the specification. So we wanted some idea that the specification actually matched up, and our initial approach was to take one of the existing tools we already had, the Angus symbolic execution engine, which was originally made for some of our concurrency work, and repurposed it to give us a test generation tool. And call it test generation tool. And the rough idea is you take some instructions, you pick out the error, or you decide you want to particularly look at right now. You ask the symbolic execution engine what the allowed behaviors of these are in a reasonable starting configuration. And you run a solver to find out, pull in any missing details and tell you what the output should be. And then you run it through the hardware. Or ARM ran it through the hardware for us because we can see the RTL. We also run it through our own simulators to do cross-checking because we're not sure that all of our SAIL backends are always in sync with one another. And we found a bunch of not really non-security related bugs in the original ASL specification. Generally, for the validation work, we found that they built the right thing, but the specification was occasionally slightly wrong. And we also found a bunch of bugs in our tooling because we'd just written it, some of it. We also found that this was a very useful test suite for developing our QEMU support for Morello. So Lawrence Eswood did this. He took this suite of tests and he found it was very easy to just go instruction by instruction, adding extra features to QEMU and checking they're functioning properly. And that provided his starting point for running work. Later on, ARM were kind enough to let us see their confidential test suite. And we found that the instruction set coverage was slightly complementary. There were some corner cases they didn't pick up on. I think this is just because they were developing everything on a much more constrained timeline than normal. They couldn't put the same resources into it they would for a production piece of silicon. They also had proper system coverage, whereas we were only really looking at the instruction set. But the problem with it is it's confidential, so you can't give it away to other people. The tests are quite large, whereas ours are very small. So if you're doing something like this QEMU work, then you've got to get a long way in before you actually get to the test. Whereas ours, you've got some simple setup, and then you run your test. So we were able to put these tests that we generate some models straight into the QEMU continuous integration. And you can make sure that you hadn't broken things along the way. That's fine. So this is one of the uses we've made of our tooling. We've now got some confidence that our model is correct. Now we may actually want to prove something about the architecture and some machine code. And this is where Thomas is going to take over. But if anyone has any questions about the spec, it would be a great time.
Yeah, for the translation from ASL into sale.
Yeah.
So you said it was fully automatic?
Please.
Was it fully automatic, or did you need to do some manual intervention, and how long does it take?
Yeah, so this is a process that we've been using for some time before this. And it's a bit of both. So the languages aren't quite the same. The Sail has a much stricter type system. And so occasionally you want to patch things to make the type checker happier. So we've got an automatic translation, but it will stop occasionally and say, nah, type checker is failing here. So maybe you want to go away and patch it. And sometimes you do patch the function it's complaining about. Sometimes you patch a function it's using to give you more information. So that was our main interaction. There are other places where we decide to override parts of the original specification to make it work better with other parts of our tooling. But mostly it's automatic. It has to be automatic. The specification is far too large.
Oh, so it's automatic, although you need to do things manually, under change from the original spec. If changes come through or systems change, then you can.
Yeah, and it's relatively stable. Our only main problem, I think, was when there's some automatic generated ASL from for system registers, and some of the function names in there have hash codes, and every so often they regenerate that from whatever upstream database there is, and all the hash codes would change, and you get a bit confused. But because most of the our work was excuse me, didn't care about these functions didn't specifically refer to these functions, they just dealt with them automatically. It just made diffing things hard. It's mostly fine.
Alright. So let's talk about a whole ISA arbitrary code property that we proved about Morello. And this part of the work is something that we mostly done a few years ago while the Morello architecture was still being developed. And some of you might have heard about this already, but I think it's still worth going about talking about it, both in its own right and also because we are now building on these properties and connecting them to the work that Angus is going to talk about to enable reasoning about combinations of known and unknown code, where we use these properties that we proved here to put constraints on the behavior of the unknown code. So what's the property that we proved? Intuitively, the key property that we want to capture here is that when you run arbitrary code on Morello, it is constrained by the capabilities that you give to it, and it cannot forge any capabilities that it shouldn't have access to. And we formalize this using this notion of reachable capabilities, which you can think of basically as an upper bound on the set of capabilities that we think software should be allowed to construct from the capabilities in a given starting state. So this is defined inductively by taking the capabilities that the software immediately has accessible in registers, and then capabilities that can be loaded from memory via an authorizing capability that is already reachable, and then capabilities that you can derive from that using monotonic operations. So you can take away privileges by shrinking the bounds or removing permissions, but you cannot grow the privileges of capabilities. And then what the theorem says is that this is actually an upper bound. So when you have a sequence of arbitrary instructions, then the set of reachable capabilities does not grow along the states, along the strings. So in other words, there is no magic sequence of instructions that software can use to forge a capability that was not already reachable from the starting state. And this monotonicity property holds up until certain points. So there are certain non-monotonic transitions that we have to take into account. For example, if there is a processor exception or a system call and control transfers to the operating system, then the operating system will typically have a different set of capabilities reachable to it. And then there is also a mechanism that Morello provides for securely transferring control between pieces of software that might be mutually distrusting of each other, using a mechanism called sealed capabilities. And you could use that, for example, to call into another software compartment without giving it access to your own data. And that might also constitute a non-monotonic transition. And I'm not going to go into much more detail here, but the formalization of this spells out in detail under which conditions these non-monotonic transitions can occur and what exactly is allowed to happen in those cases. But up until that point, monotonicity holds under certain assumptions. So we have some assumptions on the system state. In particular, we assume that the address translation mapping between virtual and physical addresses does not change under our feed, because these capabilities, they carry virtual addresses. So if you were able to change the translation mapping, then you could basically change the mean of capabilities. So we assume that that does not happen. All right, so how do we prove this? One step is to break down these whole ISA properties into smaller and much more local properties of the individual instructions. And here we arrived at some pretty straightforward properties that say, for example, that every time an instruction performs a memory access, then it must have already obtained a capability that authorizes it. And every time an instruction writes a capability to a register or to memory, that capability must have been derived from capabilities that it already had. Again, with some well-defined exceptions in this case. So here again, we have to specify in detail what these non-monotonic exceptions are. But then these properties together, they imply this whole ISA security property. And you can also see this more generally as an abstraction of what any instruction in any cherry ISA must satisfy. So you could see this as an abstraction of cherry ISAs that you could build upon. So our working title for this abstraction was T-cherry, or a theoretician's cherry. So this is some very narrow abstraction of what instructions in cherry ISAs can do. And then in order to prove this, because these properties are relatively simple, they are also relatively straightforward to verify for concrete ISAs like Morello. And another design decision that we made that I think makes this more straightforward is the shape of the model that we use. So we look at the semantics of instructions in terms of the register and memory effects that they generate. So our semantics gives us for each instruction, and as a matter of fact for each auxiliary function, the set of possible event traces that it can generate in terms of register reads and writes and memory accesses. So for example, here we have a PC relative load instruction, and it can generate events like, okay, read the capability from the program counter capability register, then derive an address from that and perform a memory access, and then write the capability that has been read to the destination register. And there are many more events in here, so for checking system registers and performing address translation and so on. And there might also be other traces. So for example, if the capability check for the memory access fails, then instead of performing the memory access, the instruction will raise a processor exception. So originally, this interface was designed to connect the instruction semantics to relaxed memory models, but we also found this very useful to formulate the properties that we need in a succinct way. So we can then say, for example, that for any possible trace of any instruction, if it performs a register write of a capability, then this capability must have been obtained legally before. So in this case, this capability has just been copied from the one that has been loaded from memory. And then for checking the memory access, we have to make sure that this address here is within the bounds of a capability that instruction already has, which in this case is this C capability here. Right. So this seems pretty straightforward, although if you would then want to actually prove it for the concrete ISA, you have to do quite a bit of work. So one thing we had to do is we had to prove manually a number of lemmas about some key auxiliary functions in the spec, in particular the ones that deal with capability manipulation. So for example, changing the bounds of capability. And what makes this tricky is that capabilities in Morello use a compression scheme to be able to fit both a 64-bit virtual address and the bounds and permissions metadata into 128 bits. And this representation of the bounds uses a floating point-like representation. And that is a bit tricky to reason about. So these functions alone, verifying them, took us quite a few person months. So that was quite a bit of effort. And then we have the whole rest of the architecture to deal with. Morally, you might think this shouldn't be too hard, because basically what you have to check is that all the instructions use these primitive helper functions correctly. But going through the whole spec in an automated way requires quite a bit of proof engineering. And we wrote some custom automation for this. We did not try to do very fancy automation. We just followed some pretty straightforward approach where we had some custom proof rules for breaking down the properties into smaller ones that can be verified, and having a tool that basically automatically generates lemmas for all the auxiliary functions and instructions in the spec, and some custom tactics that prove those lemmas. So this was pretty straightforward, but it worked well enough for us. So yeah, it was in the end quite a bit of effort, as you might expect for wrestling with a very large specification that has some complex parts. In total, for the main proof, we spent about 2 person years. This was Thomas Sewell and myself, who both worked on this for an average of about a year. And we managed to finish the proof in that time, and that was a good thing, because a bit more than a year was about the time we had between receiving the first snapshot of the specification and the architecture being frozen and moving into the hardware manufacturing phase. And we wanted to finish this proof before the silicon gets finalized. Because any bugs that we found, we wanted to report them and have them fixed. And we did find a couple of bugs in here. Some of them we found very early on, even before we started doing the Isabel proof. We used some of the SAIL SMT tooling to check some properties of these capability manipulation functions, and already found some bugs there. And then later throughout the proof, we found a number of bugs, mostly missing capability checks in some of the corner cases of the architecture. We did not find very many bugs, which is, I guess, a sign of the quality that the designers of the architecture at ARM were doing. But yeah, so from our perspective, I guess it was a pretty successful story that we managed to finish this proof of an industrial scale specification within the constraints of an industrial project. So we're quite happy about that. Of course, there are some limitations of this work. So this is just about the architecture specification, not about the microarchitecture of the actual Morello chip. We don't consider side channels or concurrency in this work. There are some trusted computing base, like the translation into Isabel. And there's some more detailed discussion in the ESOP 2022 paper, if you want to look into more detail on this. I guess for the purpose of this talk, the main limitation is that while this is an essential security property that you definitely want, if you want to reason about actual code, then you need something more. And for that, I will hand over to Angus.
Yes, I have a question on the arbitrary code that the theorem applies to. I'm a bit surprised. I would have thought that because of the compression function, you rely on that code not allocating chunks of memory that are too small. Because if you allocate something that is too small or not aligned with the limitations of the compression scheme, then you may have a capability that is to access the next allocation. So is it where is it captured in the fork or in the specification?
And I guess if you try to have a too small allocation,
small allocations, the compression scheme is such that small allocations are precise. So up to something, I forget from Morello, I think it's maybe 16 kilobyte allocations, you don't get any lossiness. There's no alignment constraint on the lossiness. Sorry, there is a small alignment constraint, but it's not what you particularly aggressive. So it's for the next like factor of 2 size of capability, you lose 1 bit of precision. You can only have even bounds, then multiples of 4, multiples of 8, but with any position in memory. And the lossiness is always conservative, so you can't sort of rederive a capability somewhere where the compression scheme is going to make it bigger somehow. It'll always make it smaller. That might be, it might cause your program to crash because you've lost access to some memory you meant to have access to, but it's never unsafe. And if you're careful, you can avoid that ever happening just by not deriving capabilities that are the wrong size. And this is not too egregious.
One thing that helps here is that you can, it's quite reasonable to go to, well, you have to change your memory allocators anyway to actually use capabilities properly. So to do that, you make sure that they allow for extra padding. If you're allocating something large.
So you need to fix the allocator to avoid crashes because of that issue. But it doesn't affect the security of the design.
So of course, you probably at that point would be large enough you're allocating entire pages at a time. So it's obviously not that hard to avoid crashes.
So one of ARM's favorite hobbies is just adding bunches of instructions. So you developed some automation to deal with the instructions you had. Do you reckon it's sort of complete enough that future instructions would just be checked by the automation, or is it sort of specialized to what you have?
it might just work here, especially if the instructions don't do very fancy things with capabilities, then it might just work. If not, then you might have to tweak the automation a bit. So this lemma generation tool that we have, it allows some manual interventions where you can say for specific instructions use these additional lemmas or something like that. So with that, you should be able to get a look.
Our guess would be that something like the scalable vector extensions would probably be fine. Something like the memory copying instructions might need a little bit of work.
Okay, so limitations notwithstanding, T-Cherry is really a very strong constraint on the behavior of arbitrary code, and that's super useful. But it's really not obvious how you can use it to prove the correctness of some concrete program. So to give an example of the kind of thing, a toy example of the kind of thing you might struggle with, consider this little toy program. It allocates a reference cell and then provides you a function that lets you increment it, modulo 1000, and returns the current value. In a memory-safe language, it's reasonably obvious, unless I've written a bug, that the value is between 0 and 100, always. If you expose this to somebody who has machine code access, that's not true, right? They can guess the pointer that is storing this reference cell, change it to whatever value they like. So the question is, can we recover the sort of the safety property on a Morello system, and can we prove that we can recover it? So we expect that this should be possible, principally because of a project called Cerise by Georges et al. From Aarhus, which formalizes a secure cooling convention for a very simplified capability machine, which lets you prove statements approximately of the form expressed in Iris if your domain boundaries are correctly protected, and you can prove that your code locally preserves some invariants on its own memory. Those invariants remain true even when interacting with adversarial code. I should mention there are a bunch of different flavors of Cerise. We're building on only the very simplest, so we're not thinking about stack protection or any of the exotic capabilities that later versions of Cerise dealt with. So before, implicit in this is you need to be able to reason about known code at all. Right, you've got a concrete program in front of me, I want to be able to prove it protects its own invariants. We know for the ARM architecture, purely for reasons of scale, this is very challenging. We have a cock model of the ARM architecture. It's almost impossible to reason with at the moment. The theorem prover tends to just fall over if you try and load it. But a project that I worked on with Michael Samler a couple of years ago called Bauereiss significantly simplifies this. Sorry, I lost track of where I am in my slides. Yes. So Bauereiss, yes.
So I didn't quite understand what you said. I heard some of the words. So the ARM spec was large.
The ARM spec is extremely large.
It was hard for you to carry out a proof about the ARM system using your tool because of the size of it. I didn't understand why.
So if we have the ability, we have a model of the ARM ISA in Coq. It's a few 100,000 lines of Coq. If you try and this might not be true anymore, but certainly at the beginning of this project it was the case that if you tried to load this into the theorem improver and just sort of run simple on a completely concrete program, it would just crash. Didn't even have the opportunity to run out of memory.
I see. So the tools weren't up to the task.
Yes.
Okay.
There's not a lot of semantics of this scale that people are reasoning about in theorem improvers like Coq. You do it a bit better in Isabelle, but that means some of what we're doing here depends heavily on Iris to give us the strength of program logics we need to express some of these properties. So that locks us into using Coq or something like Coq.
You think, I don't know exactly how it compares to other large Coq projects like Concert or something. I don't know what are the largest Coq projects. But do you think it's
Repeat the question, please.
Yes, is it just the mere size of the spec that's the issue, or also the way that things are encoded?
It's almost certainly some of both. I will say it's not, when I say it's very, very large, I don't just mean it's a lot of code in total. It's effectively one top-level function that you actually want to unfold, right? Or not to unfold, but to execute, right? It's not that the hook model consists of 100,000 lines of proof, which is no longer that amazing. It's that it's sort of one, sort of the execute the ISA function is 100,000 plus lines of code, and that's not a thing I'm aware of anyone else really dealing with.
I would say that our Coq backend is now better. It's producing digestible models, but we just don't have the machinery you need to break it up and reason about. Whereas we already had the stuff that I'm talking about.
Yes.
Could you solve the problem just by buying a bigger computer? You haven't said anything about how much memory you've got. Or...
I don't know which of the largest computers we've got that I've tried building it on. I think I've tried to run this on a machine with 100 gigabytes of memory and it ran out. I'm aware you can buy more memory than that, but you really shouldn't have to prove that like a 5-instruction program executes correctly.
Machines with a terabyte of RAM.
Sure, but I don't want to have to need a terabyte of RAM to prove that like adding 1 to a register adds 1 to the register. I feel like I should be able to do that more simplistically, and we can, so that's good. So the way that we do this is the Solaris project works by taking this very large specification, taking some knowledge you have about the program you're trying to reason about. The two biggest things are, if you know what instruction you're executing, you can throw away the rest of the spec. And if you know what exception level you're in, you can throw away an enormous quantity of the spec, because very often you're reasoning about a program running at EL0, you don't care about the system's features, they shouldn't influence anything. Knowing about something about the memory translation helps a lot. Yes?
Yeah, so you say you can throw out pieces. You can't throw out the memory translation, though, because that's what Cherry and the memory management is all about.
So one is, yes, we do throw out the address translation. There's a couple of justifications for that. One is, if the operating system's doing its job correctly, you hope that, and admittedly...
So it's not a model of the machine, it's a model of what you might think a user process is in a Linux or something. In other words, it's an idealized machine.
Okay, so there's a few different ways of thinking about it. One is you can treat it as an idealization. The other is you can turn the address translation off on ARM. That's a reasonable mode to run EL0 in, especially in embedded settings. And especially if you have Cherry, Cherry doesn't depend on address translation, right? Cherry gives you memory protection even without address translation. So running in the identity address map on Cherry is actually relatively reasonable.
Okay, so so you said that ARM you can turn the memory management off?
You can make it be the identity, which is...
So it's still there and it's still doing the mapping. You just assume that it's okay.
You can have a register configuration that causes the mapping to be the identity. You don't need to have it translation tables that actually make it the identity, you can use register configuration to enforce that.
You can turn it off.
Okay.
No.
All right. There's a yeah. So if you know a little bit about your machine state, you can simplify a lot of the spec. And so the Alaris takes this. So we already had this simplification tooling, the ILA symbolic evaluation tool that's been mentioned a couple of times. Alaris takes that existing tooling to sort of simplify the architecture specification for reasoning about a concrete program. And we give an iris-based program logic for reasoning about the resulting simplified code. The examples of, if you have simple instructions, things that just do arithmetic on registers, they really do go from this enormous unwieldy specification to one line of read this register, compute this value from the read value, write that value back. And you just get one sort of line of pure arithmetic reasoning. The problem with Alaris is almost all of this complexity win comes from knowing what instructions you're executing. And if you have an adversary, you have no idea what instructions they're going to be executing. And Alaris is almost unusable, or was almost unusable in this state. So the project we've been working on is Morello-Cerise. Morello-Cerise consists essentially of two parts. One is the existing Alaris automation for reasoning about your known code. So you take the code, your own code, verify it using Alaris, somewhat modified, but with basically the same interface that it had before. And we also prove a logical relation, as a Cerise-like logical relation that proves that your unknown adversarial code can't damage memory addresses that it shouldn't have access to. And the logical relation expresses this in a way that makes it easy-ish to combine with your correctness proof of your known code and get a sort of overall correctness theorem that your invariants aren't violated at any point during the machine execution. We've proven the FTLR for this logical relation, and we've got a simple accumulator example, relatively similar to the one that I showed earlier. Proven modulo one or two lemmas that we're still working on exactly how capabilities are encoding, but those should be gone pretty quickly. And this whole idea is based on a sort of a novel machine semantics for the machine that gives you Alaris-like reasoning with the Alaris semantics when you know what code is executing, and a reasoning based on the T-Cherry properties when you're executing unknown code. So yes, thank you very much. Any questions about any part of the talk?
I'm not coming up to ask a question in the session. He's looking at me like I got something.
Yeah.
So I'm curious how you decide the boundary between the known codes and the unknown codes. Is that a user choice?
So in Alaris, in pre-existing Alaris, you specify upfront what instructions you expect to be at what addresses. We've just augmented that with, now you can specify that an instruction has unknown code at it. And it's easy to say that you have that for every address other than the addresses that you know. And then mechanically in the program logic, essentially this is, you get the trace, you start executing the trace of an arbitrary instruction constrained only by the T-Cherry properties. And then you could reason about that directly, or the whole point is you can just use the FTLR to say that's enough to know that everything is safe.
Sure. So Morello has like a bunch of mechanisms to sort of encapsulate your code and then expose it to sort of unknown adversarial code.
Mm-hmm.
I presume your logical relation captures sort of one approach to this?
So we capture two of them well. We have, so unlike Cerise, we have to capture all of them at least a little bit, right? The Cerise setting just, they imagine a machine semantics that only has the ones they want to reason about on any given day.
Very convenient.
We can't do that. We have to deal with Morello, which has 5 or 6 of them. And so we have to give at least some reasoning principle for all of them. But many of those are intentionally trivial. And 2 of them we handle well. Like you actually, you can encapsulate code in such a way that it can do non-monotonic.
So do you mean, from the point of view of known code, there's two you support, and from the point of view of unknown code, you have to cover all the cases because you don't know.
Yeah, you have to prove that you have to prove that none of them can be used to do unsafe things. Two of them have a property strong enough that your known code can use them to sort of give access to itself in a safe way.
Okay. I guess
the two are sentries and indirect sentries.
I guess the follow-up question is, how much of a pain would it be to sort of support all the wacky other ones?
Conceptually, none of them are that bad. In practice, they're all just a little bit annoying in ways that makes you not want to deal with them. The sort of pair invocation would be relatively easy. You just have to I dropped that one at some point because Morello, unlike Cerise, technically lets you unseal sentries if you have an unsealing capability, so it was easiest to prevent that just by preventing unsealing capabilities. Points to pair has an annoying behavior where you load two capabilities and you have to care about them. You can't, it's a little bit annoying to stop you loading the left capability of one pair and the right capability of another pair. But they're all possible. Like I had sketches of all of them at some point and didn't deal with them just because they turned out to be unnecessary.
Can two capabilities have overlapping requirements on a region of memory?
Capability, do you mean in the machine or in the proof? I guess is the.
I guess in either or both. I'm just curious, sure. As a programmer, could I say this is read only and then somewhere else say that it's read write or something like that? What kind of consistency checks do I have across?
So capabilities don't give you don't constrain memory. They sort of give permissions. So in that case, in that sense, it's additive. If you have a read-only cap for some region of memory and you have a write-only cap for some region of memory, and you are careful to use the right one at the right time, you can both read and write that memory. In the proof, that setting up that scenario is kind of annoying, but it is possible. You end up with what look like different invariants on the same memory, but in fact you have to sort of show that what look like two different invariants on the same memory are actually instances of the same invariant. But it's possible, it's just a pain.
There's also some slightly more advanced features that we haven't played with, which allow you to do things like, say, this capability only gives you read-only access to both it and anything you can reach from it. So if you give it a linked list, even if the links within the list say they're writable, you only get read access to everything. So there's some really clever stuff. I don't know how well used it is.
There is also, in the original things that say about overlapping, you can absolutely have two capabilities, same piece of code can hold them, that have overlapping regions in memory. One might be inside the other, they might be separate, just have some intersection. But you have to use them intentionally. So this is part of avoiding confused equity. I have some code that, in principle, the logic says, yes, you can access all this memory, but unless it does so with the correct capabilities, it will not succeed.
So, but let's say you had two capabilities of the same character. Could you spread your linked list across two capability regions?
Yes, because each link just has a capability for the next place. So when you're building, you have to derive the correct capabilities for each link from the appropriate one. You can certainly have a linked list where if you have access to the tail of it, you do not have access to the head. If you have access to the head, you have access to the whole thing.
Okay. Sounds hard. All right, well, thank you.